means once we have defined Coriolis coefficient in this other way, we can observe that basically our total power associated with the flow is given by the specific weight. Observe that right before, maybe also in your slide, there wasn't the specific weight, but it was my mistake, I have to say it. And then is multiplied by the branches, where inside you have the something that is really similar to the total head associated with your flow, except for the presence of the Coriolis coefficient. And everything is multiplied, so it's exactly this expression right here, because it's the kinetic power plus this term, and everything is multiplied for the volume times the volumetric discharge. This term inside the branches is the total head average associated with the flow. So, in the end, for a linear flow of ideal fluid, we can say that if the power is constant and the volumetric discharge associated with the fluid is constant, then the average total head is again constant, which brings to the extension to Bernoulli's theorem for a linear flow of an ideal incompressible fluid in gravitational field. So basically, we have started from studying Bernoulli's theorem only along each trajectories. Then we extended this discussion to a finite surface, and basically we can say that it's exactly the same result of only one trajectory, but it depends on your kind of flow that you are observing. So for example, if your flow is turbulent, then this total head is exactly the same of the one that you can observe along each trajectories. If it's not like a laminar flow, then this can change. Let's try right now to see an application of Bernoulli's theorem applied to flow in the case of Bernoulli's of Coriolis coefficient equal to 1. This case is called the Venturi meter. The Venturi meter basically is an instrument where just knowing the lecture of this instrument right here and knowing the difference of the section that you observe from moving to this section right here to this one, then you can directly know the flow, the volumetric discharge, which passes along your pipe. So basically you have a convergent, so you are moving from a cross-section D1 to a cross-section D2, which is smaller. Moving from these two cross-section, if the area, if the section decreases for the continuity equation, it means that the velocity associated with the flow increases. So moving from D1 to D2, you will probably see that right here you have a velocity which is really smaller than this one, and it's explained in the picture right there. So we are again assuming that your fluid is ideal, so the energy line or total head is constant. But your piezometric line, which is the total head, in some sense is the total head minus the kinetic height, so basically this line describes only Z plus P over gamma. And you see that your pressure decreases if the velocity increases. So, how to study this thing? Basically, we have to consider two facts. The presence of this instrument, which is called a differential manometer. Differential manometer is an instrument that allows you to evaluate the pressure on the section where this instrument is linked. So basically, from the lecture of this section, you can directly know the difference of piezometric line between section number 1 or section A to section number 2 or section B. So basically, from capital delta you can find delta, so the difference of the piezometric line. Then, applying Bernoulli's theorem from point A to point B, we will find out another expression of this little delta. So, comparing this one, which is the definition, or better, there's of course a way to evaluate this relationship of the differential manometer to the Bernoulli's theorem, just comparing these two and reminding that the continuity equation is still valid, you can say that the total discharge, the total volumetric discharge associated with the fluid is given by exactly these formulas. And let's see why. Alright, so we said that we want to study this flow. So basically, we need to apply Bernoulli's theorem from section A to section B. Just reminding the picture that we have seen before. So, basically, if I apply Bernoulli from point A to point B, I will have ZA plus PA over gamma plus the velocity in the section A to the power of 2 over 2g. And everything is equal to, of course, again, we are assuming that the Coriolis coefficient is almost equal to 1, and everything is equal to ZB plus PB, the pressure on B over gamma, plus VB to the power of 2 over 2g. Then, let's see what's happening. So basically, if I consider the difference of the two piezometric line, I will add that this is the piezometric line associated with the section A, while this one is the piezometric line associated with the section B. Of course, this one, from what we studied, is the total head in point in section A is equal to the total head on section B. So basically, let's try to get HA minus HB. HA minus HB in our scheme was exactly equal to delta. But what is equal also to? It's equal to VB to the power of 2 minus VA to the power of 2 over 2g. It's just an equation, so from this one I will get exactly this one. And this is the first equation that we have to take into account. Then we have to consider the definition of the differential manometer, or better, the relationship related to the differential manometer. So basically it says that the difference among each piezometric line on the section where your manometer is linked is equal to the ratio among the difference of the specific weight m of the specific weight of the manometer fluid inside your instrument minus the specific weight of the fluid that you are considering over gamma times capital delta. So I would compare this one with this one because are exactly the same equation. So 1 equal to 2 brings you, and considering that the Q, so the volumetric discharge, is constant, which means that the velocity in cross-section A times the area of A is equal to the velocity in cross-section B times the area of cross-section B. And if it's valid, let's compare. We will get VB to the power of 2 minus VA to the power of 2 over 2G equal to gamma m minus gamma over gamma delta. Else, this one, from this one, I can say, for example, that VB is equal to VA AA over AB or and QA, for example, is equal to one moment. So let's see what we get. So basically we will have VB explained like Q. So it's VB, it's Q to the power of 2 over AB to the power of 2 minus VA to the power of 2 is again Q to the power of 2 over A to the power of 2 over 2G. Alright, so it becomes gamma m minus gamma over gamma delta, and then Q2 that multiplies 1 over AB to the power of 2 minus 1 over AA to the power of 2 equals to 2G, again gamma m minus gamma over gamma times delta. Okay, so almost finally we have Q to the power of 2 that multiplies AB to the power of 2 times AA to the power of 2. So it's AA to the power of 2 minus AB to the power of 2 equal again to 2G that multiplies gamma m minus gamma over gamma times delta. And finally you get the expression of the volumetric discharge Q, which will be AB times AA over square AA to the power of 2 minus AB to the power of 2. Hope this is clear. That multiplies square to G gamma m minus gamma over gamma times delta. So basically you obtain something where your volumetric discharge depends only on the cross-section ABAA, the specific weight of your fluid, so gamma is the specific weight again of the fluid that moves inside your Venturi meter, while gamma m is the manometer fluid inside your instrument times delta, which is exactly the lecture that you find from the differential manometer. Alright, so here you find exactly the formulas that we have just seen. So basically, let's go on. You have also other kind of fluid flow meters. Usually flow meters are something that allow to evaluate the discharge inside the pipe by forcing your flow to pass through a bottleneck. So a little restriction in your section, and from this restriction you increase the velocity, and in this way you force your fluid to decrease its pressure, and you can measure this decreasing of the pressure again with the manometer. So basically, in general, an increase of velocity is combined with a drop of pressure. So basically, if you move from, like in the Venturi meter, from one section to another one, in this point where you have the convergent, you will have an increasing of the velocity, but at the same time a decreasing in the pressure. This could be a problem because this drop of pressure is translating into a problem which is called the cavitation problem. Alright, let's try to solve this exercise, and to do this I have to just recall for a while the exercise that I have scannerized. So basically this is the exercise associated with the Venturi meter. So basically you have a pipe where inside you have a fluid which of course is moving. Then this fluid passes across a convergent, and you assume that you don't have any energy losses. Then you get to the section D2, and you can observe again that moving from D1 to D2 it decreases the cross-section area, which means that the velocity associated with your flow, so the volumetric discharge, increases. So in this section right here, where you have D1, you will have a velocity which is really smaller than the velocity that we'll get here, where you have D2, because D1 is greater than D2, which means that V1 is lower than V2. But if in D2 you have a decrease, again an increasing of the velocity, the pressure tends to decrease. So your data are that D1 is equal to 1 meter, D2 is equal to 0.5 meter. Then you know the pressure in section number 1, which is given by 2 bar. Then you have the specific weight of the fluid moving inside your convergent, which is water, and you have also the fluid inside the manometer, which is mercury. Then you also know the lecture of your differential manometer, and what you want to define is how much is the volumetric discharge inside your pipe, first. Second point, how much is the pressure in section number 2. Again, we assume that the head losses are negligible in the convergent. Then we say we do exactly what we had done before. So basically we define the difference between these two hydraulic heads, right, 1 and 2. So we apply Bernoulli from section number 1 to section number 2, assuming that the fluid is turbulent, so assuming that the Coriolis coefficient is equal to 1. Then Then, if H1 minus A2 is exactly equal to delta, but H1 is Z1 plus P1 over gamma, and A2 is Z2 plus P2 over gamma, then also we can say that, as we said before, if everything is constant, we have also to remember that Z1 plus P1 over gamma is also equal to, say, H1 minus 1 to the power of 2 over 2g, is exactly our hydraulic head. So, this one minus this one, but it's valid Bernoulli's theorem, which means that the total head, the energy line, is constant, so H1 is equal to H2, which brings that delta is given by, again, Q2 to the power of 2 minus 1 to the power of 2 over 2g, which again is 2 to the over A2 to the power of 2, continuity equation, minus again Q2 over A1 to the power of 2, so basically again continuity equation over 2g. So it's just another way to write what we have written before. So basically right here you have Q to the power of 2 over 2g, and again you collect 1 over A2 to the power of 2 minus 1 over A1 to the power of 2, and again is Q to the power of 2 over 2g, and you combine better this expression, remembering the relationship among delta, capital delta and delta of your differential manometer, and just putting equal this term with this one, you again reach this stuff. So Q is exactly the expression that we have found before, and it's equal to 0.451 meters to the power of 3 over second. Same things if we want to find P2, which means that we apply Bernoulli from point 1 to point 2, and in particular in this way, if I apply Bernoulli's from 1 to 2, we will have to consider that we assume that, for example, the reference system is the same, so the geodetic height is equal. Then it brings you that one is equal to the 2 and it goes away, and then P2 over gamma is equal to P1 over gamma plus 1 to the power of 2 minus Q2 to the power of 2 over 2g, and rearranging, if I multiply times gamma everywhere, I obtain this formula. So basically, if you just make some computation, you obtain that your pressure is 1.97 times 10 to the power of 5 Pascal, or 1.97 bar, which again demonstrates you that your pressure from 2 bar, it's again decreasing because your velocity right here is increasing. Alright, so let's try to generalize the Bernoulli's theorem. So basically, we want to express Bernoulli's theorem in two cases. The first one is the presence of machines. What are machines? Suppose that we want to move the fluid from a point to another, where the first point is characterized by a lower energy. So physically it's impossible to move the fluid from a lower kind of energy to a higher one. To do this, you need an energy contribution from outside, from another thing. And this is done exactly by introducing a machine which brings a higher contribution of energy to your fluid. So basically, you insert pumps. So pumps are machines that increase the energy of your fluid. So basically, for example, alright, sorry for 1 second. Alright, so basically, right now we have seen this stuff. We have said that in ideal fluid you have that your total head is constant, so it's valid Bernoulli theorem, which means that if you move, for example, from point 0 to point S along a pipe, so this is your pipe and this is the sense of the direction of your fluid, then for Bernoulli theorem you have that h along each point S, so your pipe goes on, for example, is exactly equal to h in 0. So this is the situation for Bernoulli theorem ideal fluid. What I would try to say, so this is your first case. In the second case is, suppose again that you have an ideal fluid, but for example, it's just a generic case, you want to move your fluid from point 1, which is a tank at a certain level, to point 2, which is a tank to a higher level. And physically this is not possible because you want to move the fluid in a direction where the energy associated in this point is of course higher, and unless here you have a pressurized tank, so the pressure is higher again and gives the necessary energy to make your fluid moving from point 1 to point 2. But suppose that it's not the case and you want exactly to move the fluid from 1 to 2. So usually what you can do is insert a pump, and the pump basically increase. So suppose that again you have a ideal fluid, so it increases of course till the point of A2, so this part does not exist, sorry, my drawing is awful, but it increases the energy to allow the fluid to move from point 1 to point 2. So basically this stuff right here, let's try to see it better, is the first part of your Bernoulli theorem, and this part in this way becomes HS. Again, because we are moving from point 0, which is somewhere along your pipe, to point S, which is another point in your pipe. So HS, the final point, is equal to H0, so the first total head that you see, plus delta HM, where M stands for machines. So delta HM is equal to, exactly the amount of energy given by the pump in this case. So in this case HS, if I, for example, see 0 right here and S right there, HS will have a higher energy respect H0. So delta HM is greater than 0. There's also another situation. The other situation is when, for example, you want to get energy from your fluid. And this is the case, for example, of hydroelectric plants. So basically, to your fluid, there's an energy which is associated with it. So you want to take part of this energy and convert this energy into other kind of energy, like electricity one. So basically, suppose that in the second case you have something like this. So for example, you have a tank number 1, and then you have the pipe, and you have the tank number 2. So with level number 1 is associated a kind of energy which is higher to number 2, which means basically that moving from 1 to 2, you can get part of the energy associated with the fluid. So for example, if it's again an ideal case, right here I insert a machine, and this machine takes part of your fluid. Suppose that my drawing is better, so it's awful, but from the slide it's better to see it. So basically you will have that right here your energy decreases till this level in tank number 2. Alright, so this part again is your delta HM. So right here it was an increasing, right there will be a decreasing. So basically again, if I move from point 0 to point S, I will have that H, the total head in point S, is given by the total head in point 0 minus, plus again delta HM, but in this case delta HM it's negative because you take the energy from your fluid. So again, we have the Bernoulli's theorem for an ideal fluid. We have again the case of an ideal fluid with case number 1, you take the energy. Case number 2, case number 1 and case number 2, so here you give the energy, right there you take the energy because right here you increase the total head, while right there you decrease it. Let's right now see what happens, for example, when you have to consider a real fluid. So let's go back for a second to the slide.